Welcome back, guys, to our second segment. We're still talking percentage composition. We want to understand chemical formulae. So our focus now, we shall shift it a little bit to focus on percentage composition, to say what percentage of a certain element is present in a compound. This definitely has to be compounds. Why? Because we're talking about different elements forming up a substance, and these elements are actually chemically joined together. Let's locate that. So we are talking percentage composition in as far as chemical formulae. Okay, right. Now the question is, how can you tell what quantity of each element is found in a compound? So we can think of expressing, the amount or the quantity of each element in terms of percentages, right? So the answer to that, or the thinking, is that actually the chemical formula gives the ratio of moles. Okay, very, very important. It's the ratio of moles, because quantity of matter is actually in moles, okay? So of elements in a compound. So the chemical formula gives us the ratio of moles of each element in a given compound. So another measure is to express that as a percentage, which has to do with percentage composition. Right. Okay. So what exactly is percentage composition all about in as far as compounds are concerned? So the proportion of each element present in a compound can be determined by making use of a chemical formula. So we need to understand the chemical formula, or we need to have the correct chemical formula for us to be able to correctly determine the percentage of each element that makes up a compound, okay? And also we need the relative atomic masses as reflected in the periodic table. So from the name, we've got the chemical formula, and then we can, after that, determine the percentage. Okay, so the mass of each element is expressed as a percentage of the total mass. So it's the percentage of each element based on the total mass of the compound. Right. Okay, now the calculation of percentage composition involves the ratio of each element relative to the molar mass of the entire compound. Okay, so when we talk about the molar mass of the entire compound, we are saying these different elements, we look at the correct chemical formula and begin to add. But remember, in some cases, there can be more than one atom, per formula or per molecule of an element. So we also need to take that as well into account. So over and above, we are saying that the percentage of an element in a compound is the ratio of atoms multiplied by the relative atomic mass divided by the molar mass expressed as a percentage. So if the moment you start multiplying by 100, we are actually determining the percentage, okay? Take note of that as well. Okay, here's a question for argument's sake, just to try and drive that point home. It says here, determine the percentage composition of sulfuric acid. So where do we start? We start with the correct chemical formula. Okay, so in this molecule, or this substance of sulfuric acid, we've got 2 hydrogen atoms, okay? These 2 hydrogen atoms, all right? What else? We know that there is 1 sulfur, okay, atom, and there is 4 oxygen atom. So this can only be correct provided the chemical formula is also accurate. So the starting point of determining percentage composition actually starts from identifying the correct chemical formula. So in the first segment, we managed to look at, some of the examples of how exactly we arrive at the correct chemical formula of a given substance, given the name, given the cations and the anions. Now we are able to try and put together those two so that we come up with the correct chemical formula. Then the chemical formula actually will give us an indication in terms of which elements make up that substance. And then from the subscripts and whatnot, we are able to say, okay, then if for this element there are 2 atoms, for that element there is X number of atoms, then this sets the way for us to be able to actually determine the percentage of a given element in a compound, okay? So now the other thing also that is very, very important is the molar mass of that substance. And the molar mass is also derived from the chemical formula. So when we say 2 multiplied by 1, we are saying the atomic mass of hydrogen is 1, but there's 2 of them, hence we multiply by 2. Now, each sulfur atom has a mass of 32, okay, grams per mole. Each oxygen has a mass of 16, but there's 4 of them. So the total, the molar mass of this compound, which is sulfuric acid, is actually 98 grams per mole, okay? Now, so if we were to determine the percentage composition of each of those elements that make up this substance, we've got hydrogen, sulfur, and oxygen. So for hydrogen, we'll say 2 multiplied by 1. 2 in terms of there's 2 of them, but the mass of each one of them is 1, okay? Divided by, okay, 98, okay? The 98 here is actually the total, which is 98 grams per mole, okay? If we multiply this by 100, it will actually give us the percentage of hydrogen that is present in sulfuric acid, okay? So if we go to our calculator, what do we have here? We've got 2 divided by 98, okay, multiplied by 100. So we're going to express this as a percentage. So what does that give us? 2,04, okay? So the percentage of hydrogen here is 2,04, right? 2,04%, okay? So this mass of hydrogen expressed as a percentage is 2,04. What about sulfur? Sulfur is actually 38, okay? The molar mass of sulfur, we can just verify it's 32, okay? Just to be correct. We got that from the periodic table, but there's just one sulfur. So it's gonna be 32 over the total, which is 98, multiply that by 100, it will give us the percentage. So if we focus, we draw attention to our calculator, okay? We've got 32 divided by 98, okay? Multiplied by 100. Okay, this gives us what? The percentage of sulfur, which is 32,65. Always 2 decimal places, okay? 32,65%, okay? And then last but not least, oxygen. Now, if we go back, oxygen, we said 4 of them multiplied by the mass of each one of them, which is 4 multiplied by 16 over 98. We multiply that by 100 because we want to express the mass of oxygen as a percentage, okay? This gives us what? If we go again back to our calculator, we will get 4 multiplied by 16, okay? Divided by 98, okay? We'll multiply that by 100, okay? This actually gives us the percentage of oxygen, which is 65,31, right? 65,31%. You can immediately tell that in that 98 grams per mole, a greater proportion is of oxygen. You can even tell from the formula, there is 4 atoms of oxygen, or the ratio is 4, is 2:1:4. So the greater percentage of this molecule or this substance actually is made up of oxygen and some sulfur and very little of hydrogen, because based on its mass, hydrogen is a slightly lighter, atom than the other 2, which is sulfur and oxygen, right? Okay, so that's our percentage composition. Here's another typical example, which is very interesting, okay? It says here, a sample of hydrated copper 2 sulfate, okay? The formula is given, okay? Hydrated, it means that it has got water of crystallization. So if you focus your attention on the inside there, you'd realize that the blue one is the hydrated copper sulfate, okay? So this is our hydrated copper sulfate, okay? So this copper sulfate contains water which has formed those crystals, okay? That's hydrated copper sulfate, copper 2, all right? Okay, so hence this is the formula. It has got water molecules. So the 5 which multiplies the formula of water, is actually the component that represents the water of crystallization. And then on the other end, excuse me, we have got the one that appears white in color. What exactly has happened here? If you burn the hydrated copper sulfate, you actually remove or eliminate the water of crystallization. Then it forms the very same white substance, which is an anhydrous copper sulfate. Okay, anhydrous, it means without water. Okay, so this is the white in color, which is copper sulfate without the water of crystallization. So this other one will be Cu, okay, SO4, okay, but it contains the water of crystallization, while the other one does not. Okay, so what is the percentage of water in copper 2 sulfate crystals? Okay, that's what we want to determine. Okay, first of all, we need to be in a position to determine the molar mass of copper sulfate, including the water, and then after that we are able to determine, to say what percentage of that is actually water, right? So that's what we want to do, right? So the molar mass of hydrated copper sulfate is, so the molar mass of Cu SO4, okay, SO4 5H2O, okay, is, if you go to your periodic table, you'll get 249.69 grams per mole, right? So that's the molar mass. But we want to express the percentage, the water of crystallization, as a percentage of that. So the molar mass of water of crystallization in this case, so it's going to be a molar mass of the 5, this is the pentahydrate H2O, okay? In this case, what do we have? We've got the 5 times 2, okay, all right, plus 5 multiplied by 16, okay? Then what does that give us? Okay, this gives us 5 multiplied by 2, which is a 10, plus, okay, the product of 5 times 16, of 5 and 16, okay, all right. So this gives us 90. So the molar mass of this 249.69, 90 grams per mole is actually the water of crystallization, right? So if that's the case, what are we saying? We are saying this is 90 grams per mole, which is the water of crystallization. Then if we want to express that as a percentage, it's obviously going to be 90 divided by 249.69 multiplied by 100. So whatever we get is actually the water of crystallization. Okay, so in this case we've got 90 divided by 249.69, right? We'll multiply that by 100 so that we get the percentage. The percentage is 36.04, right? So the percentage is actually 36.04%, right? So that's the idea there, okay? And then in a case where we've got nitrogen found in an element such as ammonium nitrate, we want to determine the percentage of nitrogen. We first of all start with the correct formula, which is NH4, the cation, okay? Because the nitrate is actually -1, and the ammonium ion is also +1. So there is no need for us to actually have the brackets. So that's the formula. Okay. Now the molar mass of this is actually equals to, so the molar mass of ammonium nitrate, NH4 NO3, is equals to 80 grams per mole. So you'll get this from the periodic table of elements. Okay. Now in this compound, we know that the molar mass is 80 grams per mole, right? And then in this molecular formula, there are 2 atoms of nitrogen, which each one of them has 14. So if we want to calculate the percentage of nitrogen, okay, it's actually equals to 14 multiplied by 2, because there's 2 of them, divided by the total, which is 80 grams per mole, multiplied by 100. Okay, so what do we get from that? Okay, so if we go to our calculator, we get 14 times 2, which gives us a 28 divided by 80, right? Okay, so we're going to multiply this by 100, which gives us 35%. So what does it mean? It means that 35% of this 80 grams per mole is actually nitrogen, okay, 35%. Now, what does that tell us? It tells us that in 100 grams, okay, of ammonium nitrate, okay, of NH4, okay, NO3, okay, what are we saying? 35 grams is actually nitrogen, right? Okay, so in every 100 grams of ammonium nitrate, 35 grams is actually nitrogen in terms of percentage composition. So that's the main idea. And now in a 10 gram sample, we know that 35% is actually nitrogen. So to actually find the mass of nitrogen in a 10 gram sample, we'll say, okay, 35 over 100, because for every 100 grams, 35 grams is actually nitrogen. This will multiply by 10, which is the actual mass, okay? So we'll actually get a 3.5 grams, okay, of nitrogen. So what does that tell us? 3.5 grams is actually, 35% of that. So if we are to calculate 35% of 10 grams, we'll actually get 3.5 grams, all right? So that's all about chemical composition, but it also tells us that the chemical formula of an element or compound, it gives the ratio of moles. We've driven that point home, of an element that makes up a substance, okay? So in percentage composition gives the ratio of masses, expressed as a percentage, and also percentage composition is a measure of the moles of element for every 100 gram sample. I hope it makes a lot of sense for now. Let's take a short breather. When we come back in our third and final segment, we'll take a look at the empirical formula. Let's take a short break for now.